So if you're an electrical engineering student, you're likely going to take a little class called Signals and Systems. And that's good. It's an important class and it's applicable in a lot of different areas. But if you're anything like me, you may have found yourself with a bit of a problem. Signals and systems is hard. You've got coordinate shifting, convolution, timescales in the range of infinity, the frequency domain, sampling theory. Did I mention everything's kind of a vector now? It's a lot to process. And you may just feel like your brain's about to explode. Now, you may pace around wondering if there's an easy analogy to get started with to get your footing before diving into all that. And there is. There's an analogy that really helped me understand what's going on, and I'm hoping it'll help you out too. So grab some chips and sit down, because we're going to explain the basics of sampling and phasors by entering the world of propellers. Typically, when talking about signals and systems, we're talking about sampling of voltage, so this seems like a bit of a random place to go. But have you ever watched a video of a plane propeller starting up? You may have noticed it appear to spin in one direction, slow down, and start spinning in the other direction. Weird, right? Well, this is where we get into some basic sampling theory. Now, imagine you've got two things, a camera and a propeller, and this propeller is spinning at some unknown frequency. So you come up with the idea to take pictures at a constant rate and then flip back through them like a flip book afterwards. That way you can watch the propeller spin around, and knowing what rate these pictures were taken, you should be able to guess the rate of the propeller based on that. And to simplify this, we're only going to pay attention to a single blade of the propeller. So let's say the propeller is spinning at half a rotation per second, and we're going to take pictures at 3 images per second. Well, let's start taking pictures. Here we can see the path of the propeller in real time in red, as well as what we see in the image we took at that moment along the trace. You'll notice the path of the propeller here is a sinusoid, specifically cosine, because when we started, the propeller was sticking straight up, like how cosine equals 1 at 0. With your new images, you go and flip through them at the same 3 images per second rate, and lo and behold, it appeared to take 2 seconds to get all the way around. From that, you can conclude it was spinning at half a rotation per second, or 0.5 hertz. But would this work every time, or were you just lucky? We'd better try it a few more times to figure that out. This time, let's try when the propeller is spinning clockwise at 1 rotation per second, and take pictures at a rate of 1.2 images per second. But this time, if we look at the images along the trace, we can tell something went wrong. It appears to only be spinning slowly at 0.2 rotations per second, but also in the opposite direction. If we look at the trace, we can see the propeller is not quite getting all the way around by the time the camera takes another picture. What we've stumbled upon here is known as the Nyquist criterion, which states repetitive waveforms can be correctly reconstructed provided that the sampling frequency is greater than double the highest frequency to be sampled. Or more simply in our terms, to accurately tell the speed of the propeller, we need to take pictures at twice the speed of the rotation, or faster. But then we run into an interesting question. What if we don't do that? Well, with Harry Nyquist rolling in his grave, we decide to try taking pictures at the same rate as the propeller. Well, now it appears to be stationary, which kind of makes sense. The propeller gets back to its original position at the moment we take the picture. Let's do one more. The camera now taking images at 0.8 images per second. And alright, you may be starting to notice a pattern here. This time, it appears to be spinning at 0.2 rotations per second, and this time in the same direction as in reality. Looking at these 3 results, you may have a revelation about our example about videos of propellers starting up. In that example, there is a camera taking images at a certain rate, since that's how videos work. But the propeller's rate is increasing over time. In that example, we go through each of these 3 stages. The propeller starts spinning slower than the camera rate, then catches up to it and appears stationary, and then exceeds the camera rate and appears to turn around. What we've discovered here is known as aliasing, where the apparent frequency we find is the difference between the real rate and the rate we sampled at. If we sample faster, but not quite the Nyquist frequency, we'll get a negative frequency result. And if we sample slower, we'll get a positive but slower result. Aliasing is generally something you want to try and avoid, but there are useful applications in areas such as radios, where you want to try and slow down the radio frequencies down to the audible frequency range. We could talk a lot about aliasing, but I want to move on by turning this analogy around. I made a comment before about how the propeller example seemed a bit random, but it's actually a direct parallel to phasors. In particular, the phasor e to the j omega t. This special phasor rotates around the complex plane at a constant rotation rate omega with a constant magnitude of 1. Now the exponential with the imaginary j in there is a bit hard to follow at first, so we can apply Euler's formula on it, which simply gets cosine of omega t plus j sine omega t. This looks a bit more familiar. Before, we tracked the position of a propeller and expressed its path as a sinusoid. Now, let's turn that around. If I gave you this graph and told you, hey, express this with a propeller, you may be able to say, oh yeah, I can do that. That looks like a cosine, so we just need to track the vertical position of the tip, and if it needs to get all the way around in 1 second, we'll give it a frequency of 2 pi. And I would say, yes, yeah, good, now do this one. You may have to think about it for a bit, since this one is a sine and we've only worked with cosines, but after a while you may just come up with the fact that you can track the horizontal position instead of the vertical. We can show this by rotating the propeller 90 degrees first, as if we were looking at it from below rather than from the side. And there we go, it matches the graph. We can express it as a function by showing it as sine with that same frequency of 2 pi. And I'd say, wow, you're so good. Do this one. And, well, shoot. You don't think you can do that one. A propeller can't really move like that, right? And yeah, you're right, because what you're looking at here is cosine of 2 pi t plus cosine of 4 pi t. One propeller can't express this without suddenly changing directions, but two can. And to show that, this is the part of the video where I introduce a little toy I made where we can play with this idea. I put this together in Game Maker Studio 2, simply because I had it handy and knew it was a good way to program animations visually. Game Maker Studio 2 isn't a free program, but I can export and distribute this simulation for free, which I will provide in Windows, Mac, and Ubuntu compatible forms. At the top, we can adjust the frequency of our propeller, directly corresponding to how many degrees the propeller moves each frame. Running at 60 frames per second, it currently takes about 6 seconds to get around. Currently, while the period may be technically longer, this is effectively showing cosine of 2 pi t. To express cosine of 4 pi t, all we need to do is double the frequency. But how do we show the graph from before with the sum of the two? Simple, we just need to add another propeller, which we can do by increasing the length in the second column from 0 to 2.5, and we'll reduce the original one down to 2.5 so they fit nicely on the same graph. Here, after we press set, now we see that same graph as we did before. This graph can be expressed as cosine of 2 pi t plus cosine of 4 pi t. We can do the same thing with sines as well. Pressing the arrow keys left and right, we can switch between modes, between showing cosines, sines, or both. We'll stick on both for the rest of this time. Seeing the two simultaneously gives us a good idea of the difference between how sines and cosines sum together. This simulation supports up to 6 propellers, or phasors, at once, always drawing the position of the tip of the last propeller. You can give them positive frequencies, negative frequencies, give it a frequency of 0, increase the length, or even set a negative length, which will mirror it across the axis. Isn't that charming? Having a tool like this where you can easily visualize how phasors add together can be really helpful for increasing your understanding about them. And there's a few special cases that I'd like to point out here right now. If we add two phasors, cosine of 2 pi t plus cosine of negative 2 pi t together, we see something interesting. On the cosine plot, we see the exact same plot as if we had plotted 2 times cosine of 2 pi t. However, on the sine plot, we see that the tip of the second propeller never leaves the axis, resulting in a constant 0. This is because the cosine is an even function, mirroring evenly across the y-axis, while sine is an odd function, flipping upside down across the y-axis. What if we add frequencies of 2 and 3 and their negative counterparts as well? Despite the much more complicated movement, the tip of the last cosine phasor never moves left and right, and the tip of the last sine phasor never moves up or down. This is actually something I find really fun about playing with this simulation, since no matter what order you set them in and what frequencies you pick, If you set frequencies that are conjugates of each other, this will hold true. And sometimes the movement is simply fun to watch. You can even get pretty crazy with it. The last example is a byproduct of the frequency directly mapping to how many degrees it shifts each frame. If we increase the frequency high enough, we'll start to notice some interesting behavior at a few key frequencies. At 90, we'll see an interesting aliasing effect where it looks like we're seeing the fundamental as 4 stationary phasors. Changing the frequency by 1, we'll see each of those copies rotate around as if they were rotating with a frequency of 1. And we see a neat spiraling effect on the plot. This happens at 60, 72, 90, 20, and pretty much any even division of 360. It's just another neat effect to play with. This is the part of the video where I sign off because this was supposed to be a 5-minute video, and yet here we are. I could honestly go on and on about this stuff, and I fear that trying to condense both of these topics into one video may have caused it to only scratch the surface of each. But hopefully I can stick a link to the simulation in the description of this video, and it'll be a good learning tool if you're still trying to wrap your head around how adding phasors together works. I left out a lot of the math that ties all this together, so while you may leave this video with some questions, I hope you've gained a good analogy to think about when considering both sampling and reconstructing signals out of our propellers, or phasors, which are two of the fundamental ideas behind signals and systems. Again, I hope you enjoyed it, and Conrad signing out.